Cool. Thank you very much. Thank you for hosting a lovely conference and the second week of it. So my talk today, I guess it's really more what has the Hecke category done for us. And what this is sort of hinting at is that this talk won't be, this will be, if you've got supply and demand sides of categorification, I guess I think of myself as the demand. I've never actually categorified anything, but I like the diagram algebras that come out of it. So I thought I'd start with Categorification theory, good place to start. So I'm only going to be interested in regular Categorification theory. I don't even know if this is really a terminology, but basically there'll be no singular stuff in this talk, is somehow what it's supposed to say. So I'm going to show you a coset graph and how to think of Categorification theory as walks on coset graphs. And sorry for the people who were here last week, it will be slower but quicker, I suppose. So here is a parabolic Hoxton system, namely of a maximal symmetric group product inside of a finite symmetric group. In this case, the blue transposition is the transposition of 1, 2. That is C2 inside of S5. And then there's this copy of S3 given by the green transposition, which swaps 3 and 4, and the orange transposition, which swaps 4 and 5. Okay, and what you can't quite see because I don't know how to use my Mac, is that there's a little symbol here where this guy has drawn the picture, and this is sort of following Stroppel and Brundon stuff. The idea is that the picture, because I want S2 times S3 to fix a picture, I just draw two things next to each other that are the same. Three things after that that are the same. So S2 fixes this. If you swap the first two symbols, they stay in the same place. If you swap the next three symbols, they stay in the same place. And if you don't, if you swap something else, stuff starts happening. So here, if I use the transition 2, 3, which remember is colored pink, then swapping the second and third symbol, I get something actually new. And that's all a coset is, right? It's just a way of recording coset. So I can now swap, because I've swapped the second and third, I can swap either the third and fourth, or the first and second, etc., etc., etc. So I can just draw the Brouwer graph for this Coxeter system very easily in terms of commuting little pictures. Cool. And you're probably already fine with what a Brouwer graph is anyway. So now I'm going to show you what walks in the Brouwer graph are. So you just walk. So I'm going to do pink, green, orange, blue, pink, green. And that is what we might call a reduced expression, or just a walk of minimal length, to that top guy at the very top of the graph. And what I want to do is think about how I can fold up that path to terminate at another point. So if I now do pink, green, orange, remember, that was the same color as last time, but I folded it up as Ben was talking about in his talk. You want to be able to think of, oh, there are different ways of traversing these edges. One of them is to go through. We've seen that there and there, and on the last slide. Another way is to go up and then regret something and go back to where you started. Go up and regret, fine. And you can also go down and regret. And we count these with different degrees. So the degree goes up if you're going up and back down. The degree goes down if you go down and back up. And so this actually tells you that this Categorification polynomial is Q. Why? Because it's Q to the 1 plus 1 minus 1, which is Q to the 1. Okay. So we just calculated a Categorification polynomial, huzzah. But I cheated a little bit, so let me tell you a little bit of how I cheated. So what we did on the previous slide was we picked a reduced path to that point at the very top, and then we folded it up so that it terminated at some point lower in the graph. Well, I want to talk about all these things, so I just give them a name. And then I'm going to record the polynomials that I get just by looking at, so we calculated a polynomial on the last slide, it's Q, great polynomial. Just calculate polynomial by summing up Q to the degrees of all these paths, where you fix the point lambda and the point mu, the one you started, and you consider all the ways of folding it to a given point. So the miracle of Categorification theory is that if you take this path, well, I guess it's not really a miracle. I think it's probably true in general about matrices. If you take a matrix which is unitriangular, because of course you just get to pick your favorite path, and you don't fold it up all, so you get ones on the diagonal. If you pick your, what was I saying? So this is a unitriangular matrix with entries which are just powers of q below the diagonal. So you can factorize this as something which is purely bar invariant under swapping q and q inverse, and something that is purely positive degree below the diagonal. So arbitrary matrix, if you like, can be written as q to the naturals times, okay, something of the form, how do I write it here? Something in z, q plus q inverse. Okay, and this is the definition of the Categorification polynomials, if you like. There are other definitions, but this one works just as well. And what's really nice about this definition is the one that comes really obviously from the Zergel biological picture in a way that we'll talk about shortly. But let's just calculate a few more Categorification polynomials and see how we feel about that. So here is the symmetric group on 3 letters. So I'm going to calculate the row of the matrix corresponding to that point there, which means I'm going to consider all paths to that point, and I'm going to fold up all paths that fold up to that point. And in particular, one thing you can do is just do the path to the point. And that's going to be the 1, isn't it, in our row? And ignore this for now, but we'll see. So what else can we do? We can do blue-pink. That's a path which folds up to come to our point. And I've sort of recorded this regret here as a spot, and I'm going to use spots for up regrets of degree 1 and forks for down regrets of degrees -1. You'll see that in a second. So here again, now the other guy, he can be folded up like so. So here I regretted my pink spot, and then I went up the blue. Fine. Now something a bit more interesting, I can also go all the way to the top and fold him down. So here I've got not going to do that again. Regret, do it. Fine. And notice that these have got, this is a diagram of degree 0, a path, this is just recording a path of degree 0. These are recording paths of degree 1. This is recording a path of degree 2, with no meaning attached to it yet, so don't worry too much.
So what is the difference between the two and then the big cover?
So I've picked a single reduced word, if that's what you're asking. So I've picked the word blue, pink, blue instead of the pink word pink, blue, pink. And again, I will continue to pick blue, pink, blue. And I fold him up. I can actually fold him up a different way, can't I? So this one says, okay, go up, add a degree, remove the degree. And notice that all I've done here is I wanted the color sequence of my path on the bottom of the graph picture, the terminating point, which in every case is just a single blue at the top. And all I've really drawn is the stupidest diagram to get there. That's all this thing over here records. It's just saying, okay, well, I've got blue, pink, blue on the bottom. I want it to be of degree 2. I want it to end here. Oh, I'll just stop drawing and put a spot there to remember that I stopped drawing something. Okay, so you're just recording these paths in a sort of nice, easy way. Notice here that, okay, if you're going blue, pink, blue, just a blue there, and you want it to be a degree 0, this is really the only choice you have if you want to record this for. Anyway, they're sort of nice pictures that are just coming from the paths. And actually, this is called a standard or cell representation of the Hecke category corresponding to S3. That doesn't really matter at the moment. The point is that there were 1, 2, 3, 4, 5 paths that could be folded up to terminate at blue, and there are 5 pictures corresponding to it. So let's record that as a row of this matrix that I told you to look at. So there were 5 paths terminating at the point in question. 2 of them were of degree 0. They both appeared at the top. They were the trivial one, which just went blue, and the one went blue, pink, blue. He got folded up. And all I'm going to do is factorize that matrix. And notice that, okay, sure, there's other stuff going on that I haven't done. You really need to calculate everything in here before you go around factorizing the matrices, but you can see that, of course, I'm just going to stick the 1 from here. 1 is bar invariant. It's invariant under swapping Q and Q inverse. This is all strictly positive powers of Q, and you can repeat what I just did for every row, and you get this matrix here. In fact, the only interesting guys are these ones here. And when you factorize, it looks like this. So there's only what this actually tells you is that on the previous slide, the 2 diagrams at the top were a 2-dimensional simple module for the Hecke category. Because the row of the matrix, this is going to record simples, and this is going to record composition factors, and this is going to record graded dimensions of vector spaces. But for now, all you need to know is that I made a path matrix of polynomials and factorized it just using fact-bound matrices. So there's really very little in the way. There's no categorification at this point, except that I'm trying to hint at where it's going to come in a moment. So, does anyone have any questions about Cazhdan-Lusztig form? Okie doke. So, what were those diagrams doing? I'm going to show you now how to build from any path, any map between paths, an element of the Hecke category, whatever that means. So the first thing I'm going to do is record the map from this guy to itself, if you like, the sort of trivial map from this path to itself as an idempotent. Now, the things I can do to this path are fold it up. Oh, wait, no, first thing. Notice that there are 2 ways, as Katerina said, of going around that hexagon, and I want to just be able to pick either one and move between the 2. I want to construct this category or this algebra or whatever, morphisms between paths. That's the new path, that's the old path, that's a morphism between paths. Okay, I can also fold things up, and remember, so once I folded it, I'm just going to delete it. So notice here that this path now at the top has 1 fewer blue than the one below it, and I just recorded that as a spot. And notice it's a degree 1. This is degree 1. This is degree 0. I didn't really tell you that, but this is the guy where I folded something up. I had regrets, I had blue regrets, and I got rid of them. Okay, here's another little thing you can do. You can get rid of this. Here we have a bounce down. If I want to get rid of that extra green there, I just record it as a fork. I got rid of the green, color sequence at the top, etc., etc. And so what is the point? The point is simply that you can draw diagrams as morphisms between paths. And at each point, all you're doing is the silliest diagram to make sure that you start and finish with the color sequence you want. You're just getting rid of things, wiggling things around. So you can construct these diagrams in this way. And why do they have any meaning at all? Well, here we go. Take a parabolic Coxeter system. Take the span of these diagrams and quotient out by some relations. And what you get is a quasi-hereditary algebra with Verma modules. What are these Verma modules? They're the thing that I just showed you on the previous slide. They're standard modules, cells, spect, Verma, all the same thing. They're just fold up paths so that they terminate at lambda. Look at those diagrams. That's a Verma module. Cool. And so, because we're Lie theorists, what we want to understand is the decomposition numbers. And why? Because these are easy to construct. I gave you a matrix, just a path combinatorial matrix algorithm for constructing them. And then what we really like is representation theory is simple modules. So I just want to understand the passage from easy to hard, and that's the Categorification polynomials. Or the p-Kazhdan-Lusztig polynomials, if you like, if your characteristic of which your representations are is. Okay, I just want to. Cool. Okay. Does anyone have any questions at this point about what we're up to? Okay. So we're looking at Zergel categories and their composition factor multiplicities. So here is an example of what Categorification Hecke categories have done for us. So pick any parabolic Coxeter system. Lustig and Kazhdan together conjectured that the Kazhdan-Lusztig polynomials would be composition factor multiplicities of something. They would be positive. They'd be counting something positive. And notice that a simple module can only occur in another module with positive multiplicity. You can't have -2 copies of this simple in there. So, okay, the conjecture is it's got to be something positive, but we didn't have a candidate for something like this until the past decade. You could prove these sort of results for Lie algebras and things corresponding to Weil groups, but you had no way of interpreting the coefficients of these polynomials, these matrices, delta, as something positive. So they conjectured that they would be. And lo and behold, they are. And how do they do it? Well, so the proof over C, this is very, very hard. I do not understand this proof. But you can prove that the entries, you can prove that these abstractly have positive degree powers, just like this matrix here. And this is actually for free. This is because it's cellular. It's like when you swap Q and Q inverse, it's fixed. And that's because simple modules are fixed by duality, just like this matrix here. And so you can prove the Categorification positivity conjecture by just saying, okay, well, actually, this matrix I started with was just calculating the graded characters of Bowman modules. Now, if you know that matrix, so every vector in a module must belong to some simple composition factor of the module. And so if you once you know that this is a positive degree, you already defined the Categorification polynomials to be the unique way of factorizing this. But of course, just on the level of characters, if you know that here is every vector in every standard module, and you know that all the composition factors are strictly positive degree, and all the simple modules are bar invariant, well, there's only one way of factorizing that matrix as well. So that's how you prove the Categorification positivity conjecture. Any questions at this point? Cool. So Hecke categories have already done something for us in this talk, which is good. It's halfway through. So two of the biggest questions in modular Lie theory therefore become, in some sense, one, Hecke categories, we think they're cool. We saw them do something cool already. Maybe, and sometimes I call these a lot of different things, basically because I want to tell you later that the Hecke categories control the Hecke algebra, which just seems stupid, but so I sometimes call them different things. But diagrammatic Zergel categories or Hecke categories, if you can prove that they not only are interesting in their own right, but they control everything else in Lie theory, well, then that's even more reason to study them. And okay, once you've shown that everything is a Hecke category, you then want to say, okay, well, not only am I trying to just reprove that everything is something that I like, well, I want to actually see if this gives me new information about the old things that I liked. I want to believe that the Hecke category is going to give me a new way of understanding modular representation theory. So if the Hecke category is Morita equivalent to anything I might be interested in, well, then I clearly want to understand those old things in terms of this. And that's what the rest of the talk is going to be. So do people understand what we're up to at the moment? So let's look at problem 1. I gave you 2 problems. Here's the first. So I'm going to define the affine Hecke algebra to be a diagrammatic algebra, which is just take these pictures, concatenate them on top and bottom, and use these relations. That is the affine Hecke algebra. But if you don't like that definition, we've seen plenty of definitions this week. Okay, so the Hecke category of the previous slide controls the affine Hecke algebra, which seems stupid as a statement, but let me try and point out how this works. So we like the Temperley-Leaf algebra, and we want to understand its representation theory. And its representations are labeled by 2-row partitions. And the fact that they're 2-row partitions means that you have an action by affine A1 with a parabolic A1. So partitions, why is it affine A1? Because you want to commute the rows. And you can do it, there's a shift, etc., etc. We're all familiar with this story. But of course, you want the first row to be longer than the second row, so you have to stick a parabolic to make sure you don't swap that. Okay, and then for instance, the p-Kazhdan-Lusztig polynomials that control this are just the ones that type A1. And more generally, the ones that control H row lambda mu for all symmetric groups are these ones. Oops. And so if you want to understand all representations of the symmetric groups, which is of course a quotient of the Hecke algebra, up to, so n can go to infinity here, you're not going to look at the Kazhdan-Lusztig polynomials of those symmetric groups. You look at the Kazhdan-Lusztig polynomials of something else, which acts on the representation. So I guess this is something to do with SLH. SLH hat controls the representation theory of symmetric groups. That was what Ben said at the start of his talk. And this is just saying that, yes, it does. And not only does it control the symmetric groups, so it controls any quasi-hereditary quotient of the affine Hecke algebra in terms of these regular Kazhdan-Lusztig polynomials. So I'm looking at an analog of the principal block still. And so, for instance, this. So that one just there. So that one just there is the Ringel dual of GLH. That is due to Karen Erdmann. The fact that you can, if you let P be bigger than H and look at H row partitions, it's a quasi-hereditary quotient. Sorry?
Can you say what you factor out?
Oh, so you factor out by the Young anti-symmetrizer on H+1 rows. So you're just getting rid of, so if you're looking at the image of the symmetric group in Schurwald duality, put P bigger than H, GLH, principal block, it's the other side of that picture. For the symmetric groups, but for affine Hecke algebras, you can do this in lots of different ways. One is the blob algebra, which we've seen this week. Libedinsky and Plaza conjectured that, in fact, if you take any generalized blob algebra, well, these are objects which are labeled by one row multi-partitions, so just things like this. And so what controls the representation theory of things like this? Well, it's going to be affine A2 with no parabolic, because there's no condition on these things. They're all allowed to be one row. Here, I have to have that the first row is bigger than the second, so there has to be a parabolic, a maximum parabolic for the symmetric group. But the generalized blob algebra, it's labeled by these guys, this quasi-hereditary highest weight subcategory, this quasi-hereditary quotient of the affine Hecke algebra. And because there's no first row being longer than the second row condition, it's just controlled by these guys. And in fact, you can do stuff like this. So if these are, if I've got residues here, I will use kappa. As long as these three guys are distinct, so as long as you've got different residues in the first column, that will determine a quasi-arbitrary quotient when you literally just kill everything that hasn't got 2 plus 1 rows in the center. So then, okay, this is finding a 2 with a parabolic that's a finite one. So basically, you can just play this trick of picking a given number of rows less than p, and just making sure they all start with a distinct residue, and then bam, it gives you a quasi-arbitrary quotient, and that quasi-arbitrary quotient is Morita equivalent to a Hecke category. Moreover, every quasi-hereditary quotient that factors through a cyclotomic thing works in this way. And in fact, this means that every possible parabolic affine situation, every WP of type A for any given W, the affine symmetric group, gives you a quotient of the Hecke algebra that is highest weight and realizes Zergel categories as something of interest. Cool. So, I don't know how to get rid of this symbol that's turning up in the middle of everything. So a related theorem of Elias and Lasser is that, so here, the way I managed to make this work was, this is about cyclotomic Schur algebras. And this is about, so those are well-separated weightings, box spaces. This is about plotable weightings, essentially. Because if you think about it, if I take, for example, a type B cyclotomic Schur algebra, the only way to get a quasi-arbitrary quotient, because of the dominance ordering being like, first do the first partition, then do the second partition, the only quasi-arbitrary quotient that will factor through the cyclotomic Schur algebra of type B is the thing you've already seen in type A, because you've got to say, okay, I've got to have this many rows. But if you take a different dominance ordering, so these guys are about taking different integral forms on the affine Hecke algebra for your reduction mod P, different integral forms on your spect modules. But regardless, the point is lots of regular Categorification polynomials turn up in the affine Hecke algebra, and here lots of singular ones do too. These are the only intersection of these two theorems is the symmetric group with H polymers. Cool. Did I want to say anything else? Oh, and this verifies this categorical block check conjecture of Bapat and Lipinski.
Regularly, is the middle thing proof of it's a theorem that the conjecture is true, or is it...
Yes, so they conjectured it. They conjectured the categorical block conjecture, and we said, yeah, sure, that's true, but it's also true for other stuff. So blob plus and theorem. So theorem of which part of it was a conjecture. Okay, and a lot of people have now proven that the tilting modules for general linear groups are controlled by Categorification polynomials, p-Kazhdan-Lusztig polynomials. And so, for example, if you're interested in SL3, which is a really lovely algebraic group, is controlled by this Hecke category corresponding to this parabolic Coxeter system. And in fact, oh no, everyone's on there, I think. I think that's everyone. This works for other Lie groups as well. So Hecke categories control a lot of stuff, both algebraic groups and weirder things coming from Hecke algebras, I think. Oh, okay. Are there any questions? Okay. So how and when can we calculate these Kazhdan-Lusztig polynomials with a p? So Lustig's conjecture said that the most important p-Kazhdan-Lusztig polynomials should be independent of the prime. And this was wrong. So this is an example of p-Kazhdan-Lusztig polynomials, the Hecke category, coming in and calculating something that you couldn't calculate before-ish. And I gave 3 lectures on this last week, so I'm not going to dwell on it too much. You can find me on YouTube. But the point was, what it actually did was it showed that, in fact, understanding these polynomials, these Categorification polynomials, subsumes the problem of determining prime divisors of Fibonacci numbers. So it said, okay, we can't possibly calculate these rather than we have calculated, but even showing that you can't possibly calculate them was very important, if that makes sense. I refer you to my YouTube channel for more. Okay. So what does this theorem say? It says, give up hope on calculating all Categorification polynomials for all primes. So then if you're a combinatorialist, you go, well, that's sad. And then you say, well, where is this line? This, when p tends to infinity, you can calculate these things. When p is small, and not even that small, you can't. Where is this line in the sand between combinatorial and impossible number theory? Well, I'm going to say that we're going to try and find that line in the sand for you. Really, I'm just going to do some combinatorics. So one way to do it is say which WPs are always entirely independent of the prime. And the one from the very beginning of the talk, oh, what happened? Oh, I don't know what's going on. I didn't know my computer did that. Okay. There you go. Here are a bunch of WPs where the corresponding p-Categorification polynomials are completely independent of the prime. So this is any symmetric group, take a maximal subgroup, the corresponding Categorification polynomials will be independent. And then, okay, these are different versions. A and C, B and B, stuff like that. And in fact, we actually conjecture, oh, maybe we don't conjecture, maybe we do. Question for the cop-out conjecture. These are the only infinite families of p-Categorification polynomials that are entirely independent of the prime. Of course, there are finite examples, but we think these are the only infinite ones. Okay, here's another theorem. So the last slide was which WP are completely independent of the prime. This one is the sort of opposite. Let WP be arbitrary. Which p-Categorification polynomials can I find that are, again, independent of the prime? And okay, there's always one row, one column of the p-Categorification matrix as inverse that is entirely independent of the prime, and it's the first column. And this is a generalization of Weil's character formula. Okay, cool. So I sort of justified a little bit, at least. Hecke categories are cool because they control everything we know. Hecke categories allow you to calculate new things you couldn't. Also cool. So we should study Hecke categories. I want to. Okay. So now I'm going to prove a theorem. What theorem am I going to prove? The best one. So here it is. We've already seen this one, this categorical blob conjecture. I'm going to show you how the proof works for the symmetric group, our favorite group. Okay, so I'm going to let P be 6. That's my prime. Whoa, so much all at once. What have I got here? So I'm going to show you for 3 column partitions. So this is affine A2 with a maximal parabolic of finite A2. I'm tiling 1/6 of the plane here. Why 1/6 of the plane, you ask? Because S3, the finite symmetric group, has 6 elements. So I'm taking cosets of that. So 1/6 of the whole plane going off to infinity is tiled to this beautiful text picture. And notice, okay, the first reflection I can do that stays inside my dominant chamber is pink, because pink is not in the parabolic. If I reflected green, I bleed. If I reflected blue, I bleed. So they are in the parabolic. That's what's going on over here. So this is the Hecke category. Over here, we have the KLR algebra. So notice over here, I've drawn 2 quivers. This is the Hecke category, has 3 nodes, 3 reflections. Now here I'm going to consider the prime for the KLR algebra. P is 6. So I've got 6 muted colors over here. And it's somehow some sort of like Dorothy kind of thing where you start like enjoying KLR algebras, and but then you realize you can live in muted color the whole time. And in fact, you can come over here, and they're exactly the same thing. Sorry. I didn't plan on saying that. It was just the gayest thing I've ever said. Now, I told you paths were important for the Hecke category. So how do I think of paths as having something to do with the KLR algebra? Well, fortunately, the symmetric group already has paths. What are they? They're standard tableau. And notice what I'm doing here is I'm filling this standard tableau with numbers, and that's determining the direction I'm walking in that guy on the left. So let's undo it a bit, just in case that's too fast. I've got a little thing here, 1, 2, 3. If I add the first or second column, I go 1, 2, 1, 2, 1, 2, 1, 2. Okay, now I'm going to add lots of things in the first column. There we go. Something in the second, a few things in the third. Ta-da. So that is how you think of a tableau for the symmetric group. And obviously, we know that the symmetric group really likes standard tableau in terms of paths in this geometry. And notice that, okay, here I have this sort of muted multicolor thing, tableau going on. But the important thing for the Hecke category is that I walked through a pink wall, a green wall, a blue wall, bounced on a pink, bounced on a green, and stopped. So the Hecke category only sees the walls. The KLR algebra sees all the little steps in between, and that's somehow important. And here I'm just showing you that different tableau can be obtained by folding things up. So there's some other tableau, there's some other paths, and notice, oh, one thing to notice is that when I reflect here, so if I reflect to that green wall there, the colors are preserved. So this is light gray, light green, light orange. It's still light gray, light green, light orange. It's, well, I reflected some more stuff, so there's, yeah, the colors are the same. That's the point. So the reflections in the Hecke category that I'm interested in preserve the coloring or the reflections over here. Okay, so I wanted to say that these paths morphisms should be the thing, right? So let's take two paths. There you go. They don't look great at the moment, but we'll draw a picture. So S is the path where you go 1, 2, 1, 2, 1, 2, 3, 3, 3. 1, 2, 1, 2, 1, 2, 3, 3, 3. Okay, here, this is going to be the path T where I go 1, 2, 3, 1, 2, 3, 1, 2, 3. Or just do this 3 times. So this is two paths. I want to think of the symmetric group as morphisms between paths. And how do I do that? Well, I just draw a morphism between them. Sorry?
There's a starting point of that.
Oh, all start. So the origin is here, and because I've taken the part, because the difference between these rows is 0, and I project it down onto R2, I end up where I start because the partition 3 cubed and the partition 0 cubed. Well, okay. I'm using columns instead of rows, which is probably confusing, but the starting point is the empty partition, which is near the bottom of the alcove. So this tile goes up. Okay, so just draw S along the top. 1, 2, 1, 2, 1, 2, 3, 2, 3. Draw T along the bottom. 1, 2, 3, 1, 2, 3, 1, 2, 3. Connect the 1s to 1s, connect the 2s to 2s, connect the 3s to 3s. You're done. Remember the KLR coloring, because you should. And that is, okay, I put its W, really it's an element psi in the KLR algebra, but yeah, it's a morphism between parts. Any questions about what I did there?
Is it clear which paths correspond to standard tableau?
Every path corresponds to a standard tableau, but I want to truncate and only consider certain residue sequences, and that will tell you exactly which tableau I'm interested in a sense.
In that stage with the
Yeah, so a standard tableau is one that never leaves the dominant chamber. So let's construct something. So let's construct an idempotent. So here is the tableau corresponding to that path. Great. So what I'm going to tell you is that the idempotent in the Zergel world, which just seems that I walked through something pink, goes to any path will do, but I picked my favorite one, which just walks to there. There it is. If I picked any path which only goes through this hyperplane once, I get the same thing. It's not a big deal. I could have walked all the 1s, all the 2s, all the 1s. That would have worked too. But pick any idempotent that only goes through a pink line once, only touches a pink line once. That will give you an isomorphism from the Zergel world to the Hecke world. And of course, I can go through more hyperplanes by adding more steps in the path, and there you go. idempotents, which are of course just things where you draw straight lines, go to just things where you draw straight lines under this like paths and tableau thing. Cool. Let's look at something more interesting than an idempotent. So there were braids before, right? I can go around this guy in two different ways. The blue-green way. Okay, there you go. So I'm going to go around this guy in two different ways. But to get there, I had to first do an idempotent, so I've done that. So I've walked to this point, and now I have to go around it in two different ways. I walked through a pink, so I recorded that, and there's the tableau thing. Okay, so I can go around one way. And this path goes 2, 1, 2, 2, 1, 1, 1, 3, 1. So I've written those across the top. I can also go around the other way, where I go 3, 1, 1, 1, 2, 1, 1, 2, 2. I've written that across the bottom. Okay. And now, in the spirit of doing stupid diagrams, on the left, you draw the stupidest diagram you could think of. You were like, I want to go from blue, green, blue to green, blue, green. On the right, you draw the stupidest diagram you can think of, which is just match 2s to 2s, 1s to 1s, 3s to 3s. And there you go. That's what we're proving is that the KLR algebra, after a little bit of truncation, is isomorphic to the Hecke category, which is also just an algebra. So it's just two algebras being isomorphic as algebras. What easier way could you possibly think of proving that p-Kazhdan-Lusztig polynomials give you decomposition numbers of symmetric groups than just showing that the two algebras are isomorphic? You then you need to show that this works with the spect modules, but that's given for free. So let's now look at a different morphism. Here we go. This is the one we've already seen, our friend from earlier. Now here what happens is I've gone up to this pink guy and I regretted it, right? So here I went up and back down, and here I did nothing. So this is going to be a diagram with nothing on it, no, just blank space. This is going to be a diagram somehow telling you that I tried to do a pink and failed, and it looks like this. So remember here, so this is actually, if you reflected that 7, 8, 9 to there, that would be the idempotent to there. And so this is really a part morphism as a part. Anyway, it's telling you that I'm folding up this spot. And so all I have to do is draw the tableau from that guy on top, or from this guy on the bottom, match things up in the stupid way I said, ta-da. Spots go to things where you've folded up the path through the pink hyperplane. Cool. There's another one, there's forks. So forks, that probably doesn't help, but it's because, so here, what is the fork? The fork is where, having gone through pink already, because you have to be on the higher side, you then decided to go through pink and give it up on yourself and like decided not to. So having done this, you do that. So this is what this path is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 18. My good student 18. So this is what I've written here is an 18-step path which goes through the hyperplane and then bounces because you have to go through before you can bounce. Here I've drawn another 18-step path where I take 9 steps to get there, and then I just go around in circles. And that tensor product is horizontal concatenation for those in the know. And lo and behold, the spot morphism for the KLR algebra goes to the thing where the stupid morphism between these guys. So notice the first bit I did here is 1, 2, 1, 2, 1, 2, 1, 1, 1. The first bit I did here was 1, 2, 1, 2, 1, 2, 1, 1, 1. So the morphism from that to itself is trivial. But then here I'm actually going to do something more interesting. So remember, this is all 18 steps, first those, then those, first those, then those. One path, a second path. And so all I'm going to do here is, again, connect things up in the stupidest possible way. And I think that's kind of all I wanted to say. So the point is that why do the decomposition numbers of symmetric groups come from p-Kazhdan-Lusztig polynomials? Because after applying some nice idempotents coming from Tableau, they're just isomorphic upon quotienting out by stuff that I don't want, which has too many rows. So this is the thing that we're all familiar with in the GLN setting, which is that, I have run out of time, but I'm just going to keep ignore that fact. This guy is in Scherval duality with the quotient of the symmetric group by the subalgebra where you get rid of anything that has too many rows. Okay, we're all familiar with the idea of working the principal block of this thing, which only works when p is bigger than h. But okay, quotienting out by too many rows is a symmetric group version of looking at the principal block. So there's this little technical thing which you might want to ask me about, but other than that, they're just isomorphic is somehow the point there. It's not so mysterious after all, and it gives you a way of transitioning to understanding what Zergel diagrammatics is about, where it comes from. You can think of it as just standard Tableau. You can think of these intersection cohomology forms, intersection forms, as simply the bilinear form coming from Gordon James's work in the 1980s, plus a bit of idempotence. So yeah, these strange and exotic things aren't so strange and exotic after all. They're really nice. I'm done now. Thank you.